today's speaker, Kei Tanaka from Japan, who is my collaborator, friend, and also whatever. Anyway, well, I met him actually, several years ago when I started the Inst project. He just joined the first collaboration meeting, even though he is not actually officially joined the Inst for whatever reason. But he was very interested in Inst project, and even now, he is interested, and we have some collaboration on the Inst sample. But anyway, so he has received his PhD from Tokyo Tech in 2012, and after that he had a lot of positions, various places in Japan and the United States. I don't remember where, but the last one is Colorado.
Yeah.
I working with somebody you may know. And then he came back to Japan in 2023 to start working at Science of Tokyo. Not Tokyo Tech. We are used to call it Science Tech, but Tokyo Tech. But now this name changed to Institute of Science Tokyo, and he's working as an associate professor, assistant professor. Okay, and today he's going to talk about hot and dynamical bursts of massive stars. So let's welcome Kei Tanaka.
Thank you, Hashi-san. Hello, everyone. Konnichiwa, ni hao. I'm Kei Tanaka from Science Tokyo, and maybe you've never heard this name, Science Tokyo, before. Maybe for some of you, maybe this name, Tokyo Kogyo Daigaku or Tokyo Tech, as Hashi-san already mentioned, might be more familiar for many of you. And our previous university just merged with another university, Tokyo Medical and Dental University, and emerged as a new university exactly last year, 1 year ago, which name is now Tokyo Kagaku Daigaku in Japanese and Science Tokyo in English. And this was my previous ID card, Tokyo Kogyo Daigaku, Tokyo Tech. And I got, of course, new one. You may wonder what the heck is it? Well, not only the university merged, but my ID card also did. So this is actually currently official my ID card.
Oh, I see.
Pretty highly sophisticated, high-tech, leading university idea, right? Well, as you see, the transition is not necessarily really smooth right now. It's still ongoing, as you can imagine. But I believe our university will establish, re-establish as a leading university in Japan reasonably soon. All right, and let me move on to science. So I've been working on the formation of massive stars. In particular, I'm mostly interested in a smaller scale star formation, like sub-parsec scale down to the AU scale, even to the stellar radius scale. And I started from my theory works as a PhD, and as Ohai-san already mentioned, I travel around in the world and as I did many postdoc positions, and I start some observation project as well, and some project I led by myself. So today I will mix theory and observation to those three topics. So today I try to talk like last 10 years work from me, and still ongoing work are also involved. So there are so many topics. So I hope, because this is my first visit here, official visit here. So I hope one of those topics will be much your interest. And I want to start some new collaboration. Okay. The first topic is about feedback. As you may know, massive stars are super luminous, and their strong luminosity radiation can actually completely stop mass accretion, which might set the upper mass limit. And the second topic is about dust and gas. We found that disks around massive stars are pretty hot because luminosity is pretty high, mass is, a gravitational potential is deep, And also accretion rate is pretty high, so the disks are very hot, and there we can investigate the ice sublimated silicate grains and also their sublimation. So we can do some laboratory experiment in there of the astromaterial science. Okay? And finally, I will extend my target to the earlier universe to test the universality or diversity of the star formation processes, I mean dynamical and chemical evolution of the protostars across cosmic history. I hope I will have time for this. Okay, let me start from the first topic, and you can stop and my talk at any point. You can ask any question if it's short. Okay, so why do I care massive stars? Of course, massive stars are very, very important, and massive stars, say about 10 solar mass stars, are rare in number. They are just like a 1%, even in a young cluster. But the individual massive stars are pretty luminous, like 10,000 solar luminosity, or even 1 million solar luminosity. So they are shiny for human eye, and they are just beautiful. Of course, they are not just beautiful. Due to their strong radiation and stellar wind and also supernovae, they basically control the dynamical and chemical evolution of interstellar medium. And even after their death, they change their form to black hole, neutron stars. Of course, they are the engine of the high energy event happening in the earlier universe. So in this way, massive stars play crucial role across the cosmic history in a chemical way and a dynamical way. That's why we want to understand their formation. At least I want to understand their formation. But the formation of massive stars are not that easy. The well-known barrier for massive star formation is radiation feedback. Okay, the first barrier is this one, radiation pressure. This is basically Eddington limit for the dusty envelope. This is a pioneer simulation by Howard York in 2002. He simulated the collapse of the self-gravitational collapse of the molecular cloud core. But when the central stellar mass reaches around 40 solar mass, radiation pressure basically exceeds the gravitational force and sweep up all surrounded material. So you cannot reach like 100 solar mass from this setup. And also, photoionization or photoevaporation is very, very important feedback in massive star formation. This is a simulation by Hosokawa-san in 2011 science paper. He simulated the first star formation, I mean like a population 3 early universe star formation. And he simulated the ionization. There's no dust rain in our universe, so radiation pressure is negligible. Still, the ionized gas is evaporated from the system because it has high temperature. And again, something around 40 solar mass, accretion completely halted by the photoevaporation. And in the present-day universe, of course, we need to think about the MHD outflow and the stellar wind, and those all feedback processes act together. However, in the universe, we know that over 100 solar masses do exist, like 200, even 300 solar masses do exist. And it's actually in the Magellanic Cloud, but still it's in the present-day universe. So how can we really form those very massive stars? So formation of the very massive star under the strong radiative feedback was a long-standing problem. I said was, that means, of course, we solved it. Not me, but community effort solved this problem basically last decade. And I'd like to show one of my paper, two actually, but with Jonathan Tan now in Chalmers and Yichen Chan in Shanghai Jiao Tong University. So we basically include all feedback processes self-consistently for the first time. This is simple star formation model, not simulation, just like a toy model. And this is scale-up version of the low mass star formation scenario, starting from core, collapse, accretion through the disk. That's it. And we calculate the accretion rate considering all feedback processes. Basically, I don't explain individual feedback to detail, but important thing is individual feedback, of course, reduced the accretion rate onto the star. And classically, people couldn't reach 100 solar mass. Oh, and just for your information, we also solved the stellar evolution self-consistently. It was important, okay? And the question was how to form over 100 solar mass stars, and which was the dominant feedback among those four. Let me show one typical result from our model calculation. Here I'm showing accretion rate as a function of the stellar mass. This is accreting system. So this is basically time evolution. And without no feedback, of course, all material just accrete onto a star. By the way, in this case, I'm showing the starting from 1,000 solar mass core. It's very massive. So without any feedback, of course, it can reach to the 1,000 solar mass. And once we turn on the MHD outflow, accretion rate drops down to this blue line, but still it can reach like 500 solar mass. About half of material just ejected from the system. And then we turn on all feedback, I mean like radiation pressure, photoionization, MH disk wind, stellar wind, everything. Then the accretion rate drops down even more. Then we got this number. So as you can see, it's much lower. Still, it can reach to the 300 solar masses. So we can actually reach 100 solar mass stars via disk accretion. So what we found was that disks are stiff enough to overcome those like multiple feedback processes consistently.
Sorry, so what kind of radiation pressure did you assume? Is it Thomson spectrum only or?
Dust radiation pressure is also included.
Okay.
So dust radiation pressure just sweep up this range of material, but that is not strong enough to destroy the disk completely. So disk itself is really stiff. Okay.
Another question. Those clouds may also depend on the mass, assuming the mass accretion.
Yeah, in our case, yeah, assume the initial cloud mass, yes.
And mass accretion, right? You have to make any assumption.
So you can imagine, like if you assume the mass of the cloud, initial cloud, and divide it by its free fall time, or just if you assume the cloud size, yeah, basically it gives you the accretion rate, yes. But the accretion, this radial accretion rate is not surprising. We are observing this type of number, so it's not too high.
So the reason why the disk can help to accumulate more mass is because most of the feedback goes to the polar direction.
That's one thing, yes. Thank you for explaining that. Yes, the radiation basically escapes to this direction, but disk side is because disk is stiff, so we cannot destroy that.
So just wondering, what is the cooling processes you model? Because you talk about feedback, right? And you have drive the wings, but you have cooling from dust on the lemon up, I guess.
Dust thermal emission is cool. This is high density region, so dust thermal emission is cooling. Yes.
Yes, because you have a cooling process that will suppress feedback. Right, you drive the wind. Actually, wind now is so strong.
Thermally driven wind. You're talking about thermally driven.
Right.
Yeah. About photoionization, I will touch that point soon. Okay. Give me a second. Okay. Now so there are so many questions. Which feedback is actually strong? So to see that, now I'm showing the mass loss rate, not accretion rate, mass loss rate as a function, again, time evolution, stellar mass. And now it's log plot and comparing the various processes. Stellar wind is negligible during the formation stage. You can imagine that. And photoionization, photoevaporation, was actually regulated. You can see it's regulated here by the dust absorption. So in other words, if we ignore the presence of dust, like the population 3 star formation, it actually takes over. We also have that type of generation. So basically the dust absorption and the releasing the thermally emitting, it's basically reduced the temperature of the ionized gas. Yes, that's the process. It was important, yes. And what we found was actually disk wind, MHD-driven disk wind, is the dominant feedback even in the formation of 100 solar mass star formation. In other words, if we just focus on the feedback processes, it is similar to the low mass star formation. So even for 100 solar mass star formation is actually scale-up version of the low mass star formation, which is well studied in the many of you here. I'm not saying like the entire picture is the same. Okay. So because we found MHD simulation is important, so afterwards we started a numerical MHD simulation of the outflows like this. But the young staff who was working on this process passed away actually 2 years ago, unfortunately. But his data is there, and we can still work on that. So even after his death, we have published the papers, and they are actually an undergrad student. So data is precious, and we have keep collaboration with him. Okay, so now feedback problem is solved, not only from my team, but afterwards from the US team, German team, and French team. They have more sophisticated numerical simulation to the high mass star formation, but there's of course small differences, and we argue something small, but the important thing is basically radiative feedback problem is now not a problem anymore. That theorist said. Is it really no problem? Of course, we do need observational tests, right? This is just like a theoretician says theoretical problem. So we do need observational tests, and we did it, okay? This work was done with Yichen Chan now in Shanghai, and we observed many high mass star forming regions, but I just want to show one case. You don't need to remember the telephone number, but the important thing is this guy is already super luminous, but still embedded in a very dense molecular cloud. And with high resolution ALMA, we see kind of interesting shape of the emission. This is 1 millimeter emission, so you may think this is dust emission. But actually it's not, because we do see the same structure in the 7 millimeter BLA observation. That means, actually this is not dust emission, rather a free emission from ionized gas. So ionized region is already created here. So the feedback is already onset as theorists, like including myself, expected. That's a numerical simulation. You see similar ionized region shape is seen there, right? And using recombination line, we can trace the dynamics in there. So recombination line basically trace the ionized gas dynamics. Maybe it's hard to see from behind, but I can just explain. It's going to the south and north direction, as you can expect from that simulation. And using the centroid map, we can see even smaller scale, like 5 milli-arc-second scale. Outflow is like going to the south and north, which is connected by the rotation at the center. And this rotation is rather now really confirmed by our follow-up observation. So you see rotation is, this blue and redshift rotation is ongoing to the east and west direction, right? It's perpendicular to the outflow direction. So we clearly see a picture of the disk accretion at the center. But this is traced by the ionized gas. So I believe at the very central region, there's a neutral gas still exists. Okay? From dynamics, we can estimate the mass, like 40 solar mass. And from infrared SED, actually those observations are also done by our team. But so from SED fitting, we can also estimate the mass, which was also 40 solar mass. So I don't say this is single star. I believe this has some companion stars, but at least dynamics is dominated by a single star, and the luminosity is also dominated by a single star. Okay? And furthermore, because we have nice data and also theoretical model, we can estimate the density, temperature, disk radius, and those physical quantities from comparison model and actual observation. And importantly, we estimated the photo evaporation rate, mass loss rate, as high as 2 times 10 to minus 5 solar mass per year. Why is this particular number important? Because this is orders of magnitude lower than theoretical simulation predicted. Simulation for the fast star formation without any dust grain. And this is exactly consistent with our dust regulated photoevaporation rate, which I explained earlier. So what I'm saying here is photoevaporation is not that important in a present day universe. Okay? And furthermore, this is kind of tentative detection, but using the 2-band images, we can make this type of index map. And as you may be able to see, some jet-like, synchrotron-like shape is seen like here. And if this is really jet, this is a signature of the disk accretion ongoing and unresolved smaller scale, the very inner region. That means the accretion is still ongoing despite the onset, after the onset of the ionized feedback. So this is exactly what theorists predicted. But this is just like a single case, and afterwards several papers just published, including ours, but there is no like self-consistent survey conducted yet. So actually we have started yet that. Okay, this is, we call HIPPOS project, that's a cute name, named after high mass photoionizing protostar object survey. And our target is a very luminous sources with a radial route, that means ionization already started. So from the systematic observation, I believe we can give a more strong constraint on the feedback process from the observation side to test the theory. And to work on this data, Suinan Jiang, who was in Shanghai Observatory, and just joined our team today. Unfortunately, I'm here, but she just joined our team from today, and she will work on this data. Okay, and the second topic is about dust and gas in hot disks, where we can investigate ice sublimation, silicate sublimation. Okay, the first topic is silicate grains. Why do I care about silicate grains? Because they are the key species for considering rocky planet formation. Okay, maybe you are more familiar with this type of picture, right? Inside the snow line, people believe that terrestrial planets are formed. So to understand this process, we need to understand their stickiness of the silicate grains, but it is poorly understood. From experiment or numerical simulation, people say different numbers for their stickiness, or more precisely, fragmentation velocity, at which they start to fragment to the smaller pieces. Okay, you can imagine in a slower collision, they stick together, but higher velocity it's just fragment to the smaller pieces. And some people say it can be like 1 meter per second, that low, or some say 50 meter per second, pretty high. There's like order of magnitude difference. And you can, as an astronomer, I would say, why not testing an observation? Well, it's impossible because protoplanetary disks around the low-mass stars, like class 2 disks, are too cold. Their dust are basically icy dust, and we cannot really test the silicate grain properties there unless EDISC data. Okay? So, but our target is a high-mass star. High-mass star, again, the super luminous, like 10 to 4 solar luminosity, 10 to 6 solar luminosity. The snow line is not here, but here, extended to the envelope region. So basically, this region is all silicate grain region inside snow line, where we can investigate the collisional and the fragmentational evolution in there. And actually, there's right now only single observation, but Joseph Miguel Guillard team reported a large grain presence in a high-mass protostar. This guy is already 20 solar mass at the center, and they reported 100 micron dust exists around here from the polarization scattering. I don't need to explain this like detail, but the important thing is, yeah, large grain do exist even in the high-mass protostars. But does it mean the disks are very sticky or not? To interpret this number, we do need theoretical model, right? So we made it. So Ryota Yamamuro-san and Okuzumi-san, Satoshi Okuzumi, in our group, we wrote 2 papers recently, published. And we developed this type of disk model, considering the heating, accretion, and also the dust evolution, including the coagulation and the fragmentation. Important parameter is fragmentation velocity. Hereafter, I will just call the V-frag, flash flow fragmentation velocity, at which the dust starts to fragment into the smaller species. And people say 1 meter per second or 50 meter per second. It's uncertain, so we just use it as a free parameter and run a simple model calculation like this. So here I'm showing the maximum grain size as a function of the distance from the central star. And without grain growth, of course, it's like a sub-micron size. But with turn on the dust grain growth, it evolves like this. So grain size can be as large as like a micron size, millimeter size. And we also calculate the disk structure, but I think I can just skip those. If you are interested, just let me know later. So once we change this V-frag fragmentation velocity from 100 meter per second to 1 meter per second, the grain size changed like this. You can imagine like very sticky one can grow to the larger grain size. For fragile one, it's just saturated at the higher level, lower level. So the grain size is basically controlled by the fragmentation. So from that, we can make some simplified analytic formula where we can just assume the size is limited by fragmentation. The equation is like this. This is not a super great, it's great, but this is not super difficult equation or anything. But the important thing is like this. If we transform this equation to this form, just put in the v frag to the left-hand side, a max to the right-hand side. Now, in the right-hand side, we only have observables like grain size, accretion rate, stellar mass, radius. So in other words, using those numbers, we can estimate the v frag. And just as a demonstration, we use this particular one single case, and just put in number like 20 solar mass, accretion rate of 10 to minus 4 solar mass per year, 100 micron, 100 AU, then we got this number. So fragmentation velocity was estimated like 10 meter per second. It's in between 1 meter to 50 meter per second, as reported from the previous work, but it's now pinned down to the single value. Well, I'm not saying this value is super correct or anything. This is just single observation, and I'm not claiming this is super great or anything. But with additional like a follow-up observation toward the other sources, maybe we can give a great constraint on the fragmentation velocity only from the observation. That's exciting, right?
So you got the A max from the polarization.
Yep.
But polarization, the polarized emission was thick, right? That's why you got the A max.
Tau equal 1-ish, yes. But let me just overreact this single number. If this number is true, then it might be implies that coagulation alone may not lead the rocky plane formation, because the grains are a bit too fragile, because the turbulence in the planetary disk around the low mass star can be as high as like 20 or 50 meters per second. Okay? So interesting thing is that, so we are just observing high mass protostars, but still gives a new insight to the rocky planet formation around low mass stars. Pretty unique way. Okay? And maybe Ohashi-san also more interested in this part. So now we have like dense grain size profile and radial distribution of the grain size, surface density, the temperature. So now we have physical model. But also to compare with observation, we need to think about how it looks at the ALMA wavelengths or something. And it is important thing because the opacity at the millimeter wavelengths can change a lot if the grain size is as large as 100 micron. You may know this, like this is opacity, absorption opacity and scattering opacity, how it changes with the grain size. And most importantly, the scattering starts to dominate in a larger grain size. It cannot be ignored. So to understand this process, of course, we do need a radiative transfer with scattering. But if you are familiar with a radiative transfer with scattering is computationally expensive. We need this numerical iteration a lot. To overcome, as an alternative approach, we recently just derived a new analytic solution for disk emission, including scattering. So this simple equation, not that simple, but not that simple, but important thing is we just need a two integral of temperature profile. Just single integration twice gives you the emission from the disks with scattering included. The paper I already submitted, and if you want, I can just share my document. And also we tested this equation with a numerical, full radiative transfer calculation. Here we just changed the disk inclination angle and also the albedo or emissivity of the dust grains. And this is a result from our numerical full radiative calculation, and this is a result from our analytic solution. Can you see the difference? Actually, error is only 5%. So even though this is like numerically like a million times cheaper, you can get the great number. So with this equation, we can explore the parameter range, like a fragmentation velocity, accretion rate, whatever. And as one demonstration, this is ongoing work with Ryota. He's running the numerical simulation of the high mass star forming disk. It's pretty unstable. But together with this, we can predict the brightness temperature. So with like open source like RADMC, it can take like day for single snapshot. But for this, you can just take 1 hour, one nap, and all done. So it's super efficient way approach. Okay. Then let me move on to the higher temperature where we can expect the refractory species start to evaporate. Okay? Now the topic is about astrochemistry, so let me briefly mention about the astrochemical background. So massive star forming region was known to be rich in the chemistry because before star formation, of course the molecular cloud is low temperature, where the dust grains are surrounded by ice mantle, where many molecules are formed in there as an ice form, but we cannot really directly observe them. Well, with JWST, people start, but it's easier to observe in the gas phase. And as I told you already, the snow line in the high mass star forming region is extended to the envelope region, so we can expect like ice sublimation in the central like 10,000 AU scale, where now we can observe various molecules in the gas phase with radio emission, and including the complex organic molecule. So this type of the object is known as hot core, and this was a great target for the astrochemistry since like 70s, 80s. And so at that time, we didn't have the high resolution, so that's why we call it core. But with power of ALMA, now it's not just core, but we can clearly see the profile, like outflow cavity and how it looks in the 1000 AU scale. But now the question is, what about in the disk scale? Disk is important to form massive stars, and this must be much hotter than the hot core region. To understand that, we again conducted the ALMA observation. So this is another target. You don't need to remember the name, but again, the super luminous target, and surrounded with 1,000 solar mass cloud in there. And this is a radio jet, synchrotron jet is seen. That means disk accretion must be ongoing at an unresolved scale. So we can expect something disk in there. In the early ALMA, the result also shows some dusty emission there, but this is like 1,000 AU scale. We don't call it disk. So with Ich and Chan again, we conducted the ALMA high resolution observation, and we got the data like this. This is a color continuum image at the 1 millimeter and the 3 millimeter. Maybe it's easier to see in this way. Before that, at the very center, we found the babies, 2 babies. Massive 2 babies. The luminosity is already high, so there are like 10 solar mass, 10 solar mass massive babies are there surrounded by the dusty envelope. And using 2-band images, we can make this type of index map again. So from the index between those 2 bands, we can separate the emission mechanism from dust emission, free ionized emission, and synchrotron shocked region. As you can see, it's separated. The central twin stars are basically ionized gas surrounded by the free emission, and it's also surrounded by the circumbinary dusty envelope, and the jet is perpendicular to this envelope connected to the larger scale. So just continuum emission already tells us many dynamics in there. That's cool stuff, yeah. But my question is, what about the molecular lines? So hot core lines like complex organic molecules, CH3CN or SO2 are clearly observed there. And it's extended to like 1000 AU scale. It's nice. But if you focus on the positions of the protostars, it's dimmer or even absorption lines. So those like hot core lines are not really tracing the disk 100 AU region. But instead, we found that we detected the new disk tracers there, very interesting lines, which are water, salt, and silicate. It's more familiar to the daily life. So let me explain this. So this water line is pretty unique because its upper state energy is like 3,500 Kelvin. Highly excited line. That means, yeah, this region must be very hot, right? And also the other 2 are not necessarily that highly excited lines. Like this one is just 30, but still concentrated this region. Why is it? Because you can imagine salt and rocks are normally in a solid phase in our daily life, right? It shouldn't be in a gas phase. Now we are observing them as a gas phase. In other words, they are maybe sputtered or maybe sublimated from refractory dust grains. And that's why it's only located in a disk, very dynamic hot region, okay? And using those like interesting lines, we can see rotation of twin disks and outflow going perpendicular to the disk rotation, So they are important tracer to investigate those like a central region of massive protostar disks. Okay, and I can skip this thing. But have you heard about salty disks before? Maybe not, right? Why is it? Because we don't know if it's common or not. There is not any report. The only one other report was done by my friend Adam Ginsberg, who is also in Science Tokyo right now visiting, but I'm here. Well, there's only 2 sources, or if we count this is 2, this is only 3, massive protostars were known to have salty disks. So to understand how common are they, we conducted an ALMA archival survey, and we found basically another salty disk there. So we found 10 salty disks out of 23 sources, so that means salty disks are not that rare, nor ubiquitous so far, but at least those images are all like, how do you say that? Physical scale are aligned, so they are all exist only 100 AU scale, not like 1,000 AU scale. Again, they are only exist in the hot disks region. And this is from archival data, so very biased data. So we cannot make like a strong constraint on there, but we could make one interesting correlation map like this. Here I'm showing the correlation between some emission line like NaCl, H2 or SIS to the other lines. And NaCl salt emission is correlated with, as you can expect, the hot water line, the 3,500 Kelvin line, and also silicon compounds, another refractory. And
so these lines come from the inside of the sublimation radius, or
it's unclear yet, but if I believe our theoretical model, it shouldn't be that inside. The sublimation line should be even smaller, like tens of AU. So it shouldn't be from there, but rather maybe those species, sublimation temperature depends on the species, and then NaCl sublimation temperature from grains are still uncertain, but if the temperature is something like 300 Kelvin, maybe that's the reason. It's no line for the NaCl, yes. And NaCl emission is actually anti-correlated with the complex organic molecule, a typical hot core line. So, why am I so excited? Let me show us this one. So, source I, the closest massive protostar disk, and this is edge on disk, rotating like this, and outflow is also seen like this. And at the very center, Tachibana-san reported ALO, alumini monoxide, which is one of the most refractory species in the universe, which sublimation temperature is like 1700 Kelvin, is observed in a 50 AU scale. So why am I so excited? Because hot disks are new avenue of astrochemistry, I would say. So extended from the hot core, which was like 70s, 80s, started 70s, 80s before I was born, and but still it's ongoing, very important astrochemistry avenue. But now we reach next avenue where we have like even hotter molecules like hot water or salt or even aluminum is there. And they are, of course, important to trace the dynamics in the central region of massive protostar disk, but also it has strong connection to the astromineralogy, or more like meteorite science. You may know this is like primitive meteorite slice, and there are known inclusions called calcium aluminum rich inclusion, or CAI, the oldest material in our solar system. And for those science, of course, they have solid material, and people are studying many things on the solid phase science. But all gas phase information is gone. But now, from ALMA and toward the massive protostars, we can detect very complementary information. It cannot be done to the low mass protostars yet. And more data is coming to our group. More. This is just showing 2, but I have more projects. And also, this is very great because with NGVLA, hopefully it will come in 10 years or so. It has like an even higher resolution and a lower frequency, and there's so many NaCl emission lines. So I think this will be our next challenge for our community. I mean, like my community, to really study this astrochemistry in there.
So said basically hot core molecule is kind of weak toward this target, right?
Well, to the 1000 AU scale, they are pretty bright. So in a total flux, they are actually dominant.
Right, but in the disk region, right?
They are more like maybe self-absorbed, or maybe they are just destroyed by the strong UV or something.
Okay, so you said that might be absorbed, but it might be because of oversubtraction by continuum.
Right. And it is still unknown, so that's why we need a model calculation, and which we just started this year, so we don't have the. So far I just talked about the hard disk observation, but what about the theory, right? For theory side, we already have the disk model, like density and temperature profile from which I explained earlier. And actually last year, the chemical network, astrochemical network database is just updated. Now they include sodium, aluminum, magnesium, and titanium. That means we can also theoretically approach those hard disk things. And we started a new collaboration with Kenji and Riken, and Kaneko-san, actually former PhD student who is now working in a private company, but he kicked off this project. Okay, and I can just show the preliminary result. This is abundance as a function of the time. This is log plot, and the time scale for disk accretion is here. And as you can see, NaCl is forming with time, and it's still not saturated yet in this time scale. And it's strongly depend on the assumed temperature. If we assume 200 Kelvin or 500, it's like a 3 order of magnitude difference there. And also it strongly depends on the grain size because it's changed the ionization degree. So it's still tricky. Sorry, yeah. So I asked Kaneko-san, could you explain the result a little bit more? Before he was leaving to the private company, and he just sent me this. How am I supposed to understand this? I was like, okay, could you explain a little bit more? And he just said, bye for now. I see we have still contact, and but still he's working in a very busy company, so I cannot expect too much from him right now. But yeah, after he left, we are still simplified model, not model, but understanding of the process of the NaCl formation. I can't explain this too much for now because I don't have time, right? Yeah, but there is some neutral network or ionization, ion network, but more is coming. Please stay tuned.
So this reaction is a grain surface reaction or gas?
This is pure gas reaction.
Pure gas reaction.
So gas reaction database is updated last year. That's why.
Yeah.
Okay, let me. I think I don't have much time, so let me just briefly talk about beyond galaxy thing. Okay, so massive stars are important across cosmic history. You know this type of picture, and starting from the Big Bang to the present universe, and metricity, of course, increases our cosmic time. So early universe is a low metricity, and low metricity massive stars are important because people believe first stars are as massive as like 100 or even 1,000 solar masses, and progenitors of gravitational wave binary and the GLBs are also believed to be low metricity massive stars. And the most massive star ever found in our local universe is in LMC, which is another local low metricity environment. So that's why I think low metricity massive stars are key to connect the present day universe to the early universe, right? So to understand this, I'm doing both theoretical and observational works. From theory side, it's kind of easy because we can just change because in theory, we can play God. So we can just change the metricity in there. And this is a model I showed earlier. And at the solar metricity case, this is a mass fluxion and at the end of the accretion. So at the solar metricity case, like 30% of material just accretes on the star, and another 70% is ejected by the MHD outflow. This is what I explained earlier. But at the lower metricity, this blue part gets larger and larger. Why is it? Because now this photoionization is more dominant feedback in a lower metricity regime. That's we chatted earlier, dust absorption is now negligible at the low metallicity regime. And this is not only from my model work, but also Fukushima-san's simulation also basically show the same thing. And what about the disk fragmentation? Because most massive stars found to be a close companion, and people believe this is formed by the gravitational fragmentation of the accretion disks. And of course, they are maybe present-day analog of the progenitors of black hole binaries. Okay, how does disk stability depend on metallicity? Again, we can just play Go. We change the metallicity with Ryoki in Kochi. I don't know how to say in English, but he was in Japan. We run the simulation starting with exactly the same initial condition, just changing the metallicity. And the disk phenomena, the fragmentation phenomena, are completely different. It's interesting, right?
Well, what makes such a difference? I know metallicity, but why?
Thank you. Cooling is very different. You can imagine in a present-day metallicity, the disks are very optically thick, so inefficient in cooling. But with low metallicity regime, the disk becomes like the optical depth is around 1, where the cooling is most efficient. Then the temperature is lower. Disk is just easy to fragment. The Q parameter becomes lower.
In this case, in the low metal environment, so harder to form high mass star because a lot of satellite form and it's prevent accretion.
Right. So my prediction was it's just like share the material to each. So if you assume like a 10 solar mass core, it creates maybe like a 10 1 solar mass stars. That's maybe. But also the initial mass function is a convolution of the core mass function and the star formation efficiency. I'm just saying like efficiency is low, but if the core mass function is top heavy, then massive stars are more common. So it's like a combination. Thank you. But here I change the metallicity like by factor of 1,000. Super low metallicity environment. But what about observation? From observation, as I already showed you, we have some nice result from the galactic massive star forming region, but they are basically solar metallicity. How can we test the low metallicity star formation? Well, we can just see outside the galaxy. So Magellanic Clouds are a great target. Actually, we also have nice work in the outer galaxy, but I don't have time to talk about it. Okay, LMC, SMC, or large, small Magellanic Clouds are excellent target to investigate the low metallicity star formation because their metallicity is like a 0.2, 0.5 solar metallicities. And you may feel it's not that low compared to the theoretical models, but still it's pretty low. Here I'm showing the stellar metallicity as a function of their age. The stars around the Milky, around solar system. And as you can imagine, the typical metallicity decrease in the early universe, and LMC, SMC metallicity comes here. So basically, we are seeing like they are comparable to the early Milky Way ancestors, maybe over 10 billion years ago. So we are seeing the time capsule there. Okay. So to investigate the star formation happening in there, I started the Magellanic outflow and chemistry survey. In short, it's so-called MAGOS project. MAGOS means wizards in Spanish. And they are my wizardry friends, Icha-chan, always here, and Takashi Shimonishi in Niigata University, and many other collaborators all over the world. And I don't need to explain too much, but basically we have a survey toward the 40 high mass protostars. Our target is high mass because they are luminous. It's easier to observe as a first step. And the resolution is 0.1%, and we use a band 7. Including those molecular lines where we can investigate the outflow and the various chemistry happening in the low metallicity environment. Again, this is just Galilee. Now we can see many outflows there. So using those CO emission, we can estimate the mass and momentum energy of the outflows like this way. I don't need to explain maybe detail, but now we can directly compare the work to the Milky Way study, the previous works done by Luke Mode, showing the mass luminosity mass relation. This is a protostar luminosity and outflow mass relation for the Milky Way is shown in the blue dot, and it's actually extended to the low mass regime down to here. this correlation is very strong. This is known for a while. And our Magos data to the LMC is shown in the blue. What do you see? Yeah, actually they are pretty consistent to each other. Even the scatter level are similar. And toward SMC, we detected with Tokuda-san, we reported the very first detection of protostar outflow in the small Magellanic Cloud. This is our first outflows in SMC, which comes here, again, on the line. Cool. So star formation is universal. Now I can write a paper easily. Oh no. To the SMC, after we continue the data analysis, we got a very strange trend in there. You don't need to believe this region, because our target is limited to the luminous one, above 10,000 solar luminosity. If I've been like this, it's easier to see. Okay? What's wrong with the SMC outflows? We don't know. But interesting thing is, everything consistent here, but only SMC goes down there. And we don't know the reason. There is some discussion, CO dark outflows or really weak outflow. There is some discussion ongoing. So we do need a follow-up observation. And Swinan will work on the data again. Okay? Just briefly, but we also detected the first SMC hot cores, which is reported by Shimoni's-san. And interesting thing is this is a abundance ratio, abundance of the methanol and SO2. And this cyan color shows the median value of the galactic source. And for SO2, you can see they have, and those yellow and red bars are showing that our LMC and SMC hot cores. And they have like similar chemistry. While for the complex organic molecule, somehow they have like order of magnitude variation. They are just upper limit, so they have like 3 order of magnitude variation seen in there. So it cannot be explained simple metricity dependence, and some new interesting chemistry is happening there. One possibility is, of course, the prestellar phase chemistry. So maybe prestellar core is hotter, or maybe collapse is happening much shorter time scale, something which we haven't understood yet. But yeah, more is coming, so please stay tuned. Okay, now the summary. So today I talk about the hot and dynamic bursts of massive stars. Massive stars are very important, so that's why I'm working on from theory and observation. And today I talk about 3 topics: feedback, dust gas, and the beyond galaxy. I don't read the individual sentences, but feedback, we can form 100 solar mass stars if you believe theory. But we still do need an observational test, which we are working on HIPPOS project. And dust and gas in the hard disks, where we have strong connection to the rocky planet formation and meteorite science, astromineralogy. So chemical modeling is starting, and meteoricity dependencies to the early universe. We found a very interesting diversity happening to the SMC especially, and we haven't understood it from the theory. At least previous theory didn't expect that. So we need update the theory and observation more. Okay, more is coming. So thank you for listening. Shay Shay.
Okay, too cold.
Sorry, I took too much. I talked too much, but.
Okay. Anyway, any question, Tanaka?
I'm curious about the 10 objects which you detect the sodium lines. Do they all have similar luminosity? That tells us if they have a similar radiation environment or not.
Thank you. So far, because the data is very biased, and yes, the luminous brightness flux are kind of similar, but it is mostly due to the sensitivity limit. So because we can see only like bright ones. So that's why I think, and some lines are not seen, maybe just due to our sensitivity is not high enough yet.
Yes. Very nice talk.
Thank you.
I have a little experience in chemical network, so yeah, we would love to look into the pathways of light.
Okay.
My question is regarding your hot core the complex organic molecules in the hard cores, what's your take on the silt line, which is the sublimation of carbons can make carbon-rich inner disks, which has been observed by JLST, I think.
Thank you for asking. Yeah, asking. Actually, before NSL, we expect silt lines, but we don't know which lines should we really see. So, if you because maybe once the carbon just released to the gas phase, it can just create a CO or something. So I don't know. What if you can tell us like which molecule is expected? Maybe we can just target on the, and probably if the silt line can be observed, temperature, in terms of temperature, I think they should be in a disk scale rather than the envelope scale, and even in high mass stars. So, but still, it should be detectable. So if you can predict the good molecule for that, yeah, it would be great.
Yeah, I think it's a suite of molecules, but the presence is probably debatable as I talk to people. Yeah, but yeah, I would like to discuss this one.
Okay, cool. Yeah, the thing is, if you see the data, the high mass for the low mass stars, maybe the lines are just like, to the high mass stars, lines are all everywhere. It's really messy. So the line contamination can be very problematic. That's also one reason why we can see only bright line.
So high mass stars are better for constraining the external line.
Sorry, could you say that?
So are you saying high mass stars are better to test the silt line scenario?
I don't need to say better, but yeah, it has advantage that the hotter region is larger, but also disadvantage that there is so many lines which can contaminate the line which you want to see. So pro and con is there. So we need to try. Thank you.
Any other questions, comments?
Just very naive question. I think that you want to detect this refractory, just want to know how much length, right, the disk. So, but based on current result, in terms of looking for the future, can you estimate inventory? Because dust can drip in, do a radial drip into the inner part. So, what's your take? Can you eventually to estimate the amount of starting material, like say, okay, because this for exoplanet communities, there's a lot of super Earths that very closely, obviously very small. But right up here is like a scale up.
Yes.
Yeah. So I'm just curious, can in the future,
So
how much even like inventory, how much budget, the mass budget?
Right, the mass budget problem. Yes, at least for the high mass protostars. We just naively assume the dust and gas are well mixed, and even for 100 micron size, they're in terms of the Stokes number, it's pretty small because the column density is pretty high, accretion phase. So we don't see like a radial migration of dust toward them. But yes, that's very important question, and to estimate the dust mass, maybe not the high mass observation, rather our analytic solution for the disk emission might help to understand to read the data to the low mass protostars. It might help to understand.
Okay. All right. So then he's going to stay here until Friday in the room 1107. So if you get
1108.
1108. Okay, sorry. Next to 1107. So if you have more questions or want to chat with him, so please visit the room, and then you are very welcome. So thanks again to the Tanaka.